Hi and welcome to Unit 2, Topic 2, Video 14, and in this video we're going to put this concept, this converting a cos x minus or plus b sin x into the form of a single cos or a single sine into use. And I've got an example here that has two parts. The first part is to do the conversion, the second part is to use the conversion. So let's go ahead and do the conversion now. Now, you note here we've done that, and we've got an and, so I need to do both. So in doing both, the first thing that happens is I get this common r. And so we know, or we recall that r is equal to the square root of a squared plus b squared, which is root 3 squared plus negative 1 squared. Notice here it's always a and b, and so b of course is negative 1. And that will be important when we come to the tan stuff. So we get the square root of 3 plus 1, which of course is the square root of 4, which is 2. Pretty common R calculation there. And then we also have to work out, in this case, the alpha. So the alpha, you recall, is tan inverse of b over a. Now it's important to note here, depending on the textbook you use or what you're following, you might find that people sometimes use sine and cos. Now you could use that sine and cos because you recall that in the previous video, we determined the alpha by suggesting that cos of alpha was equal to a over r, and sine of alpha was equal to b over r. And so we've got an r value, that works nicely, and all we have to do now is just reverse that sine and cos to calculate alpha. The good thing about doing it this way is that you can pinpoint the exact quadrant, because if cos is negative and sine is positive, well, where is cos negative and sine positive? Second quadrant. We can pinpoint that really easily. And we've got a nice easy r we've already calculated, and we have to calculate anyway. The bad thing is we have to do two inverses, so there's a little bit more calculation. Tan can work really well, and this should be tan inverse, I apologise. Tan can work really well, you only have to do it once, so I'm going to do is equal to tan inverse of b over a, which is 1 over root 3, and of course that should be negative 1, and tan inverse of negative 1 on root 3. Tan inverse, tan is, it's going to present as a fourth quadrant answer if we do that in our calculator. So I'm going to use that fourth quadrant answer, and that's equal to pi over 6, but negative. So we get a negative pi over 6 solution there. Now, our problem is that we actually get two solutions because tan inverse is negative in two quadrants. The second quadrant as well is a proper solution. So I could actually write this down as 5 pi and 6, which is the equivalent second quadrant solution that we get from this nice little unit circle. There's pi and 6, there's 5 pi and 6, which we can calculate by doing pi minus pi and 6. That's not a minus, minus. So there's two solutions, we have to pinpoint which one. Cos and sine would pinpoint that for us, we have to pinpoint it ourselves. And I'm going to do it by recognising that the b value is negative and the a value is positive. So if we go back up to our previous video, our a value is positive and our b value is negative, means that we are positive, negative, we're in the fourth quadrant. So I'm actually going to take the fourth quadrant solution. Of course, the cos and sine would fix that problem. So if you don't want to have to go through that logical process, use that cos and sine, and you would get cos of alpha equals a over r, and we know our a is positive, so cos is in a positive quadrant, 1 or 4. Sine, b is negative, so sine's in a negative quadrant, 4 or 3, so therefore it must be quadrant 4. And therefore, root 3 cos x minus sine x is equal to 2, our r, and then cos of x, and we get minus our alpha, and our alpha is negative pi and 6, so I'm going to make that a plus pi and 6. And you can have a look on Desmos, and they should look the same if I plot this or this, the same thing. Now, of course, we have got this second one, and my writing and working is getting a little bit out of hand. But let's do it again. So I'll just do a little line here to show you this. Imagine we repeat that r process, but we get r equals 2. And, of course, beta, you recall, is equal to tan inverse of a over b. We've already worked out this is a is positive and b is negative, and so it's in the fourth quadrant. So we get tan inverse of a, which is negative 1 on root 3. My apologies. got that back to front, root 3 over negative 1. And so that is pi on 3 in the first quadrant, but this is going to give us the fourth quadrant answer, which is negative pi on 3 is the fourth quadrant answer. And so we get the equivalent again, which is 2 sine x plus beta, which in this case is plus negative pi on 3, which means we don't really need that plus, so that's just minus pi on 3. Now the nice thing here is that we get this exact relationship we're expecting, in that there is a clear difference of pi on 2. So this, if we got plus pi on 6, this takes us back an extra pi on 2, which is the phase shift we expect for a sine to cosine. Okay, now we can use this to solve root 3 cos x minus sine x equals negative 1, because we've transformed this now to be 2 cos x plus pi on 6 equals negative 1, which means that we get cos x plus pi over 6 is equal to negative 1 on 2. And if we do cos inverse of that, we get x plus pi on 6 is equal to, cos is negative in the second or third. It's going to give us a second quadrant answer to start with. Cos inverse of that is pi on 3, but the second quadrant is actually 2 pi on 3. So just keep in mind, I'm playing around again with that unit circle. Pi on 3 is where we get cos is equal to a half, cos of pi on 3, but we're over here. So this is also pi on 3, but it's pi minus pi on 3 there, and pi minus pi on 3 is 2 pi on 3. We also get the third quadrant answer, which is pi plus pi on 3, and so that is 4 pi on 3. And there's our first stream of answers. Here's our second stream of answers. And now I can go through and find any subsequent answers by adding or subtracting 2 pi's. But I can see here that I don't really need to. Now I do have to be careful because I've got a little bit of transformation to go, which might take our top one beyond the upper value or our bottom one below. But I'm going to deal with that in a minute if I need to. So I subtract pi on 6, and I get x is equal to 2 pi on 3, which is 4 pi on 6, which gives me 3 pi on 6, which is pi on 2. Or x is equal to 4 pi on 3, which is 8 pi on 6, minus pi on 6 is 7 pi on 6. So there's how we can solve that equation by using this transformation. And again, I'd probably stick with the cos, it's a little bit easier to deal with, and then go back and do the sine if needed. All the best.